Hi, my name is Andrew Buck and I'm with the University of Missouri. Today I'll be presenting our paper called VADER, a hardware and simulation platform for visually aware drone autonomy research. This is a collaboration between several authors at the University of Missouri and the U.S. Army and Tim Wilkin, who visited us from Deakin University in Australia and kickstarted this whole project. So here's a brief outline of the talk and a picture of us with the VADER drone that we worked on. To start, I want to give a little background and motivation for why we felt the need to build our own platform for doing research with drones or unmanned aerial systems. I'll go over the hardware platform that we designed using commercial off-the-shelf components and open source software. And then I'll talk a bit about the simulation environments we used, which were really helpful during these work from home times. And we'll end with a bunch of examples of how we've been using these tools for some interesting research topics and take a look at some ideas for future work. So what is VADER? Basically, VADER is a framework for doing end-to-end academic research with drones or unmanned aerial systems. You know, there's lots of applications where having a bird's eye view of the environment opens up some new and interesting research possibilities, like data collection, where, for instance, we might want to collect aerial imagery to train a classifier that can identify explosive hazards from a safe distance, or mapping and scene reconstruction to try and build a 3D model of the world. And we'd like to do all of this autonomously with less manual control, so you can just tell the drone to fly up and go perform a mission on its own. And one of the big research areas going forward, we think, is going to be finding ways to work together with semi-autonomous robots or drones to accomplish some shared objective with human-robot teaming. But actually doing this requires some expertise in a lot of different fields. To get a drone like a quadcopter or a hexcopter to fly, you need some knowledge of flight physics and electromechanical control. Wiring all the systems together takes some skill in electrical and computer engineering, and writing the software to perform the detection and mapping, or to do the autonomy takes some programming ability and knowledge of AI. Now, a lot of these components can be purchased and operated without having to build everything from the ground up, but it often comes with a trade-off of not having full control over the platform. So, for instance, we could buy a commercial drone and run a scripted flight sequence, but swapping out the sensors and running our own autonomy code could be difficult. So what we wanted to do was to bring together tools from all these different disciplines and make them work together. From the physical hardware side of things to being able to do a lot of this in simulation on the computer, we wanted to show how we could use commercially available components and open source software to accomplish a wide variety of research goals. All right, so one part of the VADER framework is the physical hardware. We wanted to build our own drone platform so that we could customize and configure it with all sorts of different sensors depending on the application requirements. Here we have a high-level overview of how the hardware components work together. The drone body consists of everything in the gray box, and it communicates with a ground station running on a laptop. We chose a hexacopter design based on the Sky Hero Spider 6, which gives enough flexibility to handle heavy payloads and long flight times. The two major computer components on the drone are the Cube flight controller running the ArduPilot firmware and the NVIDIA Jetson TX2 companion computer, which runs Ubuntu and ROS. ROS stands for Robot Operating System, and it provides a generic message passing framework for communicating between all the different components. We use the Maverick protocol to communicate between the ground control station and the flight controller, and MAV-ROS to interface with the companion computer. So initially our plan was to build and fly multiple physical drones based on this design, but due to the pandemic and stay-at-home orders, we were only able to partially complete one drone. We used a lot of online resources from the individual manufacturers and some in-house expertise to do the assembly and the initial wiring and soldering. Some of the specific diameter carbon fiber tubes weren't available when we ordered the parts, so we substituted in some wooden dowels for the landing gear that you can see in these photos. We tested the motors to make sure that they were working safely and calibrated them with the flight controller using ArduPilot's Mission Planner software. And then we were able to take it out for a test flight to try out some manual control and flying a simple pre-scripted waypoint mission. So now I want to talk about the software and simulation environments for VADER. The software stack can be broadly divided into high-level and low-level systems. At the low level, we have the flight controller running ArduPilot, which takes care of all the flight dynamics and basically lets us just tell the drone to go to a certain waypoint location and it will go straight there using GPS and IMU. So that lets us focus on the high-level autonomy, which uses ROS to communicate between the sensors, the flight controller, and the companion computer. Now, the nice thing about this setup is that we can substitute in a simulated environment and flight controller for the real thing and make sure our code works in the simulator before trying it out in the real world, where we might crash and break something. This actually turned out to be really valuable during the stay-at-home orders with the pandemic, since we could still work on developing simulated scenarios without having to have access to the physical drone hardware. So the three simulation environments I'll talk about on the next couple slides are Gazebo, AirSim, and our in-house environment called PCSim. So to start, the Gazebo Simulator provides a nice integration with ArduPilot and ROS, and it can simulate lots of different robot configurations with 3D world models, physics, and access to virtual sensors. Here we're showing an example where we run Gazebo, ROS, and MAV proxy to control a simulated drone and estimate depth from a single camera. We loaded in a world model that we constructed from images that were captured using another drone and stitched together using OpenDroneMap. This gave us a 3D model that we could use in Gazebo and other programs to simulate drone scenarios in these virtualized real environments. So the drone is set up to publish a color image from a virtual camera as a ROS topic, and we've got another ROS node running on running the monodepth2 estimation algorithm on that image and publishing a depth estimate in real time. Here we can control the drone with keyboard commands using MAV proxy. And although Gazebo integrates well with ROS and ArduPilot, it has a pretty basic rendering engine. So to get better looking simulations, we turn to AirSim, which is built as a plugin for the Unreal Engine. This means that we can load up just about any environment map or asset pack from the Unreal Marketplace and use these as simulation environments. We can even fly around in cities or places where it might be difficult to actually fly a real drone. AirSim has a direct API that we can access with Python, and it can also work with ROS to control the drone and send back images and sensor data. In AirSim, we've got access to a camera that gives a color image, a depth image, and a segmentation image using the exact known distances and object labels. And we can control the drone with either simulated physics using the flight controller or use a special computer vision mode to position the camera directly. And that can be useful for some applications where we really just care more about the simulated imagery rather than the actual flight physics. And the third simulation environment is one that we've been developing in-house to begin visualizing the agent's knowledge of its surroundings so that we can work on things like high-level control and autonomy. We call it PCSim for Point Cloud Simulator, since it's based on reconstructing scenes from point cloud observations. Since AirSim gives a depth image along with a color image, we can use both of these along with the known camera pose to perfectly reconstruct a point cloud from the current drone position. If we do this multiple times as the drone moves, we can build up a dense reconstruction of the environment where every pixel in every frame becomes a point in the point cloud. Now, obviously this would lead to really huge point clouds if we saved everything, so one simple reduction is to just voxelize the environment and save one data point for each voxel, which is what we're showing here. Now we can do a lot with this kind of representation, such as figuring out where to go next or how to avoid running into obstacles. But in general, understanding how best to represent the agent's knowledge of the environment as a really high level data structure is something we expect to continue looking at with future research. So what all can we do with VADER? There's lots of different applications that can take advantage of this aerial platform for data collection and pairing that with simulation. Using a simulated environment like AirSim that can provide photorealistic imagery lets us essentially substitute the real sensor data in with simulated data. So if we want to train an algorithm, say a detector such as YOLO, or do depth estimation from a moving camera, we can start with a real data set and then use the simulated environment to generate way more data that looks like the real data, but with different augmentations that might be hard to collect, such as different locations or lighting conditions. And then we can use that larger data set to train or test our algorithms and verify that they work in a variety of situations, both on the real and simulated data sets. And one of the interesting use cases that the simulation environment provides is to pair this with augmented or virtual reality so that you can walk around in the same virtual space as the drone and explore human-robot teaming possibilities, or use augmented reality to show, for instance, a mini-map hologram of what the drone sees, or overlay some useful information to the user. And along the top of this figure are some potential applications like 3D mapping, detection, semantic segmentation, tracking, fusion, exploration, and we'll look at some of these next. Okay, so the first application I'll talk about is this idea of how to explore the environment. Here the agent or drone starts out with perhaps no knowledge of its environment and has to discover its surroundings in order to build a 3D map. It might start with some initial outdated model of the environment that it needs to figure out where to go to update that model with some new information. So the question is, where should the drone go and look next to maximize the information gain, or to achieve some specific exploration goal? And we can think of this as a multi-criteria optimization problem, where we might want to, say, pick a location that's not too far away from the current position and near the edge of the explored map and unlikely to run into anything. So the image on the right shows an example of one of these multi-criteria heat maps, where blue shows distance from the drone and red shows voxel density. Weighing these two criteria gives some candidate solution that might be a good exploration target. So following this strategy or some other approach, perhaps using reinforcement learning, we can build up a 3D model of the entire environment. And one example where this could be useful is with search and rescue. So here we have a search and rescue scenario running in Gazebo using YOLO in real time. In this example, the drone flies around in a grid pattern until it finds a person and then begins a landing sequence. And you can imagine how in a more complex environment you might want to have a more sophisticated exploration strategy, but this example is just a prototype that shows how we could tie everything together and run things in real time using ROS to trigger mission events from the sensor inputs. Another application that has a lot of interesting research potential is that of trying to estimate depth from a single camera, which could be useful for collision avoidance and other things. There are some self-supervised methods that have been introduced recently that can use deep neural networks to predict both depth and camera pose from a sequence of moving images. Basically, if the camera moves during training, we can treat it as a multi-view stereo reconstruction problem and train a network that can learn to make predictions on a single static image. Here you can see a simulated image from the AirSim on the left and a real image from the Kitty dataset on the right. And below it, you see depth estimates for these images using a model that was trained on simulated data, which is pretty good in both cases. So in developing these algorithms, it can be really helpful to have some ground truth depth to go along with the prediction. In simulation, we get the ground truth for free, whereas with real data sets, we may only be able to get a sparse LiDAR point cloud with some imprecision. So we can actually use this idea of augmenting the training with simulated data and show that it works and even improves predictions on real data sets. Another thing we can do is use the simulation components of VADER for training and testing real-time computer vision algorithms. Here we've got some synthetic imagery generated with the Unreal Engine, and we're running YOLO v5 on the images. You can see with the ray tracing enabled, it's able to pick out the main objects in the scene, like cars, trucks, and people. But just like with real data, there are some things that gets wrong, like the car in the middle image that's labeled as a truck, or the skateboard in the image on the right that's really just a person's shadow. One of the nice things about using VADER and AirSim for this is that we can get the segmented object labels to use as ground truth, which could be really time intensive to do by hand. So you can see this really can help speed up development of these types of algorithms by letting us stress test certain scenarios quickly without a whole lot of extra work. And one of the things we've been using VADER for is to help generate training data for explosive hazard detection. You can imagine there are advantages to doing this from the air rather than on the ground, but it can be hard to collect enough diverse training data to train a robust detector. So we can use VADER and Unreal to create lots of labeled training data from various altitudes and with different lighting conditions and backgrounds. And then we can fuse them all together to create a combined model or use them to help us understand where the algorithms break so that we can target our efforts into specific scenarios. And the last thing I'll mention is what we can do with augmented and virtual reality. Since game engines like Unreal or Unity support AR and VR, we can pretty easily stream what we get in the simulator to one of these headsets. This could, for example, let us look at a holographic map in our hand to see the 3D model the drone has built. Or we could explore the same environment as the drone at full scale in VR and experiment with human-robot teaming. So, in conclusion, VADER presents our vision for the possibility of drone autonomy research. And we hope that this can serve as a guide for future researchers and that it demonstrates some of the potentials of this integrated approach to using both hardware and simulation. These fields have matured now to the point where it's not too difficult to put together something like this from off-the-shelf parts and open source software. And we think that using these simulation environments to create realistic scenarios can really help speed up algorithm development for a bunch of computer vision applications. So that's it. Thanks for listening. Bye.